Let's look at some properties of logarithms. These properties work for logarithms of all bases. When we write number bases, we typically want them to be positive and not 1. When that happens, we have two important properties. The log base b of b is 1. Why is that? Well, if I think about that as an exponential, if I write log base b of b equals question mark as an exponential equation, that would be b to some power equals b. Well, since b and b are the same, the power that I want is 1. So log base b of b equals 1. So if the number that we're inputting matches the number base, we'll always output 1. So for example, log base 2 of 2 would be 1. Log base 10 of 10, otherwise known as the common log of 10, is just 1. Another property we have is that the log base b of 1 is 0. It doesn't matter what the number base is. When I input 1, I will always input 0. Let's look at why that is. Log base b of 1 equals 0 is like saying b to the power of 0 equals 1. I know that this is true for any positive number that I input. If I take any number b and I raise it to the power of 0, I will always get 1. So it doesn't matter what logarithm base I pick. When I input 1, I will get 0. So for example, log base 3 of 1 is 0. The common log of 1 is 0. And the log base 20 of 1 is 0. When I look at natural logarithms, that's just another number base, so all of the same properties apply. So if I look at natural log of e, remember that with natural log, we have an unwritten base of e. So the number base and the input are the same, just like we had before. When the base and the argument are the same, then my logarithm is just going to equal 1. And the reason for this is because e to the 1 equals e. If I take the natural log of 1, then that should equal 0. Why is that? Well, again, we have this unwritten base of e. So if I write this as an exponential, that's the same as writing e to the 0 equals 1. Same number base of e, and I swap the inputs and outputs. And of course, anything to the 0 is 1, and we already talked about that. So I know, oh yes, that makes perfect sense. Now that we've worked a little bit with computing logarithms of numbers, let's look at a logarithmic function. A logarithmic function base b is a function that we can write as the form f of x equals log base b of x. Remember that if my base is 10, then I don't write the number base. I could just write it as the common log of x. And if the base is e, then it's the natural log ln of x. So those also fit this form. In order to look at the graph of a logarithmic function, let's first recall what the graphs of exponential functions look like. So if I look at the graph of an exponential function, we'll look at the natural exponential base e. Remember that the inputs are on the x-axis, and the outputs are on the y-axis. And if I look at the points that I have, I can have any x value that you like as a point on the graph. But only positive numbers are outputs. So exponential functions have all reals as inputs and only positive numbers as outputs. Logarithmic functions are the inverse. And with an inverse function, the inputs and outputs reverse roles. So for the logarithmic function, the input values will only be positive numbers. And the output values will be all real numbers. So if I look at an example of what the graph of a logarithm base e, y equals ln of x, looks like, I get a graph that sort of a mirror image of the exponential function. Notice that for our outputs, we have all real numbers, and for our inputs, we have only the positives. Now let's look at graphing logarithmic functions. So we're going to look at the graph of f of x equals log base 2 of x. We'll begin by making a table of values. Here, our function is base 2. What I'm going to do in order to find values for my logarithmic function is I'm going to start by looking at exponents that I know of that are base 2. So we'll start with easy ones. 2 to the power of 1 is just 2. 2 squared is 4. 2 cubed is 8. But let's go down in powers. Let's look at 2 to the power of 0. I know that anything to the power of 0 is 1. And then we'll even look at negative powers. The way that a negative power works, if we remember our algebra, is a negative exponent is like putting that thing in the denominator as a positive exponent. So 2 to the negative 1 is like 1/2. And 2 to the negative 2 is a 1 over 2 squared. I take that same exponent, put it in the denominator as a positive power. 2 squared is 4, so this will be 1/4. Remember our relationship between exponentials and logs, the inputs and outputs switch. So when I input a 3 into my exponential base 2, I output an 8. So for the logarithm, when I input an 8, the logarithmic function will output a 3. When I input a 4, the logarithmic function will output a 2, right? The inputs and outputs switch. When I input a 2, I will output a 1. When I input a 1, I will output a 0. When I input a 1/2 or 0.5, my logarithmic function will output a -1. And when I input a 1/4, my logarithmic function will output a -2. So remember that our function is log base 2 of x. Here I looked at exponentials base 2. My inputs were the power, my outputs were the number. For logarithms, they reverse roles. So let's go ahead and plot these points. The first point we have has an x value of 1/4 and a y value of -2. So on my graph, 1/4 as an x value will be very close to 0, and we have -2 as an output. I'll just plot that as a point. Then I have a 1/2 as my x and -1 as my input. And I have 1 as my x and 0 as my y. Then 2 as my x and 1 as my y. Then 4 as my x and 2 as my y. And 8 as my x and 3 as my y. So we can make a graph that connects these points. An important feature to note on this graph, for an exponential function, remember that the graph gets closer and closer but never touches 0 for a y value. Here, the graph gets closer and closer but never touches 0 as an x value. On a graph in math, we call this feature a vertical asymptote.